Good afternoon, everybody. My name is Hilary Traphagen. I'm the lead calibration technician and technical support staff here at the DigiVac company, and I'd like to welcome you all to DigiVac's first webinar of 2020. Today, we'll be talking about troubleshooting vacuum instruments. Normal wear and tear, accidental breakage, incorrect setup, or simple misunderstanding can cause your gauge to function abnormally. I personally service most of the technical support questions that come in, either through phone or email, and perform probably about 95% of the repairs and certified calibrations myself. But I noticed over the course of about the past year that I consistently answered a lot of the same questions. So that's why we've decided to create and present this webinar today to address some of the issues that may arise in the lifespan of your DigiVac vacuum gauge and other vacuum instruments that use thermocouple type sensors. I'd like to remind anybody that at any point in the webinar, you can submit a question by tapping the chat button, and we'll be taking a Q&A at the very end. Today's agenda will include providing examples of common issues with thermocouple gauges and controllers, such as power problems, inaccurate readings, or problems with accurate vacuum control. Then we'll advise on simple repairs and troubleshooting in the field, hoping to avoid downtime. Then we'll review some tips and tricks on proper gauge and controller setup and usage for anybody new to our instruments or their industry. We'll be focusing largely on thermocouple type gauges in this webinar, which make up a large percentage of gauges on the market and in our product line. But we can't troubleshoot a gauge without some understanding of the technology behind it. So we'll be discussing the basics of thermocouple technology coming forward. Here we have pictured an Agilent 536 vacuum sensor, which is often paired with our gauges. The 4 pins on top of the sensor are electrically connected inside by 2 thin filaments welded together inside the sensor body. We use the circuitry of the gauge to heat one of those filaments. Then that wire will heat or cool in proportion to the amount of gas bombarding it. So more air molecules, or a pressure closer to atmospheric, surrounding the filament will transfer the heat away faster, while fewer molecules to diffuse the gas, at a deeper vacuum for instance, will keep the wire hotter. Then the other filament takes the first one's temperature, and our software interprets that change in temperature as an equivalent change in pressure, turning it into a reading that anyone can understand, and our software does the rest. One of the most common issues we tackle in tech support here is a gauge that just won't power up. So here we'll discuss some common fixes. For battery-powered gauges, we always start there. Are the batteries oriented correctly according to the sticker inside the unit? Here we have pictured the sticker inside our bullseye precision gauge showing the alignment of the battery. If they are, have you used a voltmeter or a battery tester? Even if you haven't been using the gauge, the circuit exerts a small trickle current drain on the batteries, so they may be dead inside the unit, especially if the gauge hasn't been used for a while. Even batteries that are new in the box can be dead already, depending on their age. You can use a standard voltmeter to measure the DC voltage of the battery. AA batteries are 1.5 volts, so the closer to that, the better. Sometimes when dead batteries are left inside a device for a long time, the batteries will leak and corrode the terminals, leaving a chalky white substance and preventing the gauge from turning on. In this case, the gauge must be repaired by DigiVac. The bullseye precision gauge specifically has 2 modes of power. It can run on 4 AA batteries or an external power source using a micro USB cable, the same type used to charge many Android phones. However, this cable is not a battery charger. Some customers may mistake it for one, but it's simply external power and will not replenish dead AA batteries that may be left inside the gauge. This type of setup with the USB cord is common in long-term installations such as transformer cleanouts, where the gauge cannot just be turned off to replace its batteries, as it will be logging and recording data and pressure over the course of perhaps several days. The gauge can be run just fine with no batteries in it, just with the cable alone. So try powering your gauge through the micro USB port on the top. If it turns on, your issue is with the battery power. Sometimes through vigorous plugging and unplugging, the USB connector can break loose off of the internal circuit board. And in this instance, the circuit board assembly must be replaced. But for gauges with an external power supply, such as our Model 200, 215V, and DigiVac gauges, try testing the power supply with a multimeter. Set your meter to DC volts and insert one probe into the barrel of the supply end and touch the other probe to the outside of the barrel and ensure that the supply reads the voltage written on it. If your power supply tests okay and the gauge still will not turn on, consider if you or someone in your facility has attempted to power the gauge with an incompatible supply. We see these gauges in the repair queue quite often. A person has mistaken a 24-volt supply for the appropriate 5-volt supply, and higher voltage supplies will damage the CPU, amplifier, and possibly the integrity of the printed circuit board, meaning the gauge needs to be remitted to us for repair. Our gauges have error messages built in to warn users of sensor damage, poor connections, or incorrect configurations. So here we'll discuss what those error messages mean and how to interpret our problem from there. Here we have two of our most popular gauges. On our left is our Model 200. On our right is the Bullseye Precision Gauge, and both are showing error messages. Tube is an error message shown on the Bullseye that can mean a few different things. We use the terms tube and sensor interchangeably, so the gauge is asking about the status of the tube. The gauge will show this error message if the tube is disconnected entirely, if it's been unplugged from its cable, if the gauge does not recognize the tube due to possible damage within it, or if the gauge is reading a pressure out of the bounds of the gauge's range. For the Bullseye Precision Gauge, we clamp the readings at 999,000 microns or 999 torr. So any indicated pressure above that range will cause the gauge to display this error message. These conditions also exist to cause the dashes on the Model 200. So we use the same principles to test the sensor on those gauges as well. This message can sometimes appear if a gauge is powered on at atmospheric pressure and the sensor is laying sideways on a desk. Remember that the sensor needs to be mounted upright always in order to read correct vacuum. If a sensor is lying sideways, possibly suspended upside down on an angle, or basically anything other than straight up and down, the heat generated from the thermocouple filaments will no longer diffuse into the gas correctly as it sort of pulls on one edge of the sensor. This can artificially heat those filaments and skew readings. So you can simply hold the sensor upright and the reading will adjust to atmospheric pressure in just a few seconds. This is a common technical support issue that I tackle when a customer calls with a brand new gauge right out of the box, ready to use, and is curious as to why they're getting an error message right out of the gate. Meanwhile, they've opened the box on their desk. They've not yet plumbed their sensor into whatever sort of chamber that they're pulling vacuum on, and they'll have this error message, which isn't really an error at all, just merely a misunderstanding about how to correctly hold the sensor. So if your gauge is still reading tube with the tube positioned correctly, or dashes, there may be some damage to the sensor itself. The two thin filaments inside may have come apart, and this can happen with excess vibration, contamination, incorrect cleaning, or simply dropping the sensor. We remove the sensor from the cable connector gently. Don't twist it, just hold the connector in one hand and the sensor in the other and pull gently. The VGT 500 sensor has a plastic key that can sometimes break off if it's uncoupled roughly. The Agilent 531 and 536 are fully welded stainless steel and will not break this way. And the sensor can be easily and quickly tested with any multimeter. We set our meter to the ohms setting as we have pictured on this slide, and we check the connection between each 4 of the pins. We clip either meter lead to any pin and move the other lead to each of the other 3 pins. The connection between that first pin and any of the other 3 should read between about 1.5 to 2 ohms. If any of those combinations read OL, or open loop, the filaments inside are broken and the sensor needs to be replaced. Unfortunately, the filaments inside can't be repaired And if they come broken apart, that is essentially, for lack of a better term, curtains for the sensor. So it would need to be replaced at that point. So what if your gauge is powering up and reading vacuum, but you think that the readings are inaccurate? We'll troubleshoot these gauges in the next slide. Inaccurate readings can be caused by faulty equipment, leaks, contamination to the sensor, just to name a few. So here we'll discuss some troubleshooting solutions. Most importantly, remember that the gauge will not read accurately if the sensor is not mounted upright. Double check your sensor orientation and ensure that the thread or flange are facing down. Our instruments, and thermocouple type instruments in particular, are optimized for use in nitrogen. So gases with different thermal conductivity will skew readings. This is an issue we tackle in tech support from time to time. A customer will be attempting to use their thermocouple sensor in particularly noble gases such as argon or neon, and they'll wonder why their gauge is reading so off. Well, we spoke about how we generate heat with a filament and then read the heat using the other filament. Well, the heat generated by the first filament won't diffuse into other gases at the same way that a nitrogen-rich air, for instance, breathable air, will accept the heat. There are fewer molecules and different molecules to absorb that heat, so it absorbs it differently, which skews how the gauge reads vacuum. This doesn't mean that thermocouple instruments are useless in non-nitrogen rich or ambient air systems. However, it does mean that you'll need to do a bit of conversion to ascertain what your actual vacuum level is. And at DigiVac, we can provide a comprehensive thermal conductivity gas conversion chart to figure out exactly what your gauge is reading. Next to consider is, when was your gauge calibrated last? Even a rarely used gauge used in clean, dry air won't stay perfectly calibrated forever. And since there's no such thing as a perfect vacuum here on Earth, contaminants will infiltrate any vacuum system. When foreign matter meets the sensor, it alters the wires within, creates a coating over them more specifically, and those readings will drift and become less accurate over time. This is a totally normal side effect of use and not a sign of damage. Now, perhaps you've swapped out your sensor since the last time you've used the gauge. We typically don't recommend this except for emergencies only. We consider the gauge and sensor a mated pair as we calibrate the gauge for optimal linearity with that sensor in particular. We recommend calibration of the gauge whenever a new sensor is swapped in. DigiVac can provide this service for you, or we can instruct you in a field calibration process in a pinch. If your gauge is still inaccurate, you can inspect the sensor for process contamination, such as oil, debris, or metal flakes. We use an otoscope in our facility to peek inside the sensor, which is a doctor's tool used for examining the ear, though other contamination can be seen with the naked eye or with the aid of just a lighted magnifying glass. If you find contamination inside, we recommend that you follow the cleaning instructions that will be outlined further on in this webinar. We will be putting on a full-length demonstration to follow in a future webinar, though we'll outline the 4 basic steps coming up. If your gauge is not reading as expected, it's important to consider whether or not you have the right gauge for the range of vacuum that you're reading. Occasionally, we will have a customer that may buy a gauge believing it to be accurate in one particular range and to find that it is really most useful in another. We have here displayed our bullseye precision gauge, which is a thermocouple type gauge, and our bullseye piezo gauge, which uses a piezo resistive type sensor. These gauges appear similar just from first look, but they actually read different ranges of vacuum with different accuracy. The bullseye precision gauge, as with most thermocouple type instruments, is really at its most accurate from a couple of millitorr up into about 6 torr. That's merely a function of the technology of the sensor. that is standard in terms of thermocouple type instruments, that is the range with accuracy. We consider from approximately 1 to 99 millitorr to 10% of reading. From 0.1 torr up to 2 torr is 20% of reading, or 2 millitorr. From 2 to 6 torr, our accuracy range is 25% of reading. Between 6 torr and 775 torr, we call this range continuous and monotonic, meaning that the readings will change, and they will change in one direction, but they're not repeatable and can vary a significant amount from the standard. So we don't give an accuracy spec to this range in particular. We consider our range with accuracy below 6 torr. Now, our bullseye piezo gauge is not a thermocouple instrument at all. So it excels in a totally different area. The piezo-resistive sensor is isolated and reads from 1 torr to 775 torr. So we get nothing out of this particular gauge and sensor below 1 torr, but from 1 torr to 775 torr, we call our accuracy range plus or minus 2 torr. So that's great accuracy all over a more limited range. So now we'll discuss our quick 4-step sensor cleaning process. First, we remove our sensor from our black octal connected to the coiled cable on the gauge. Remember, especially in the case of the VGT 500 sensor, there is a plastic key in the center that can break off if the sensor is handled roughly or uncoupled, or possibly attempted to twist in an effort to get it off. This is not a threaded connection, although it may look like one to the untrained eye. You simply need to hold the sensor in one hand and hold the connector with the other and pull it gently. Take your sensor, position it flange or threads facing up, and find the appropriate solvent for the process. For the Thermocouple Plus sensors, and as well as the Hastings DV6 and DV4 models, isopropyl alcohol only should be used in the sensor, as the top is a plastic component. For the fully welded stainless steel sensors, such as the Agilent 531 and 536, you may use isopropyl alcohol, or you may also use acetone. Acetone would melt the plastic in the Thermocouple Plus and DV6 and DV4 sensors, so we reserve that only for the fully welded stainless steel. Take a pipette or small funnel and pour about a tablespoon of your solvent of choice directly into the body of the sensor, and allow the sensor to stand upright and let the solvent do its work and dissolve the contaminants inside the body of the sensor. Waiting approximately an hour, you'll want to pick up the sensor a couple of times. Just put your finger over the opening and very gently agitate and shake it to ensure that the solvent is moving around. Once your hour's up, you can go ahead and pour the now contaminant-rich solvent out, and you may need to repeat this step possibly once or twice, depending on how contaminated the sensor is, until the solvent runs clear from the body. Once your sensor is clean, you'll want to just sit it and let it dry in ambient air, or it can be dried under vacuum without a gauge attached. You should not use a cotton swab or compressed air to attempt to dry the interior of the sensor faster. Remember, we've got those two very delicate filaments inside, so if they're poked with a cotton swab or blasted with compressed air, they can come apart, and then the sensor will need to be replaced. So we definitely don't recommend doing that. And once you consider the sensor dry, you can plug it back into its gauge and read vacuum. Here we'll discuss some basics of our calibration process. We recommend calibration annually for customers in medium to clean environments. Processes with higher contamination risk might require more frequent calibration, about 6 months or less. We recommend shorter intervals for customers who do heat treating, metallizing, gold plating, sintered metals, oil distillation and processing, short path customers. are very prone to contaminated sensors. So in that case, we recommend calibration more frequently than not. We realize that sometimes it's impractical to remove a gauge from service and send it to us in order for calibration. So in that event, if you need emergency field calibration, you can feel free to call us for support. We have several field calibration processes that will help to keep your gauge online if you don't have the time to send it back, and we can always assist with that. Our warehouse is in New Jersey, and we provide extremely quick turnaround times. Our calibration and repair backlog is typically less than a week from receipt, and we can always expedite on request. We offer factory calibration services under real vacuum in our fully stainless steel system with a clean nitrogen backfill. We have 3 of such systems and calibrate all gauges under actual vacuum to our own advertised accuracy specs. And NIST certified calibration is available as well, a type of certified calibration where we use certified instruments to generate a form which tells you exactly what your gauge read at all pressure points and how that corresponds to our accuracy specs. I can say anecdotally, after having worked here for coming up on 8 years now and performed hundreds, if not thousands, of repairs and calibrations in that time, I receive gauges regularly that are 10 or 15 years old and require very little maintenance over time, possibly a software update, a new cable, a broken sensor from time to time. But our instruments, with proper maintenance, can and do last for many years. So up until now, we've discussed instruments designed simply to read vacuum and not to change it. So now we'll discuss some common issues for instruments equipped with valves to control vacuum. Among these gauges are our vapor pressure controller, our DigiVac, which can be equipped with a variety of both valves and sensors for precision wide range control, and our new Concerto vacuum controller, capable of controlling vacuum on 4 separate channels with just 1 instrument and a streamlined, user-friendly interface. Ensure your pump and vacuum system are connected to the correct ports on the back of the gauge. If a pump is attached to the system port or vice versa, the gauge will not control vacuum. Listen closely to the sound of the valve solenoid over the noise of the pump. Can you hear it activate as the vacuum level approaches the set point? Make sure the gauge is connected to the right port on the back of the gauge. In the case of the DigiVac, the valve card has 2 connectors and the valve is plugged into the top. If you're using the valve to control a system that is potentially contaminated, remove the valve from the system and inspect the in and out ports for oil that may be gluing the valve closed. For multi-sensor controllers, the valve is only keyed to 1 sensor and will activate at the set point as read by that sensor. So ensure that the driving sensor is the closest to the main chamber, because that is the level that you're attempting to read in the main chamber. It stands to reason that the sensor is as close to that chamber as possible. Also ensure that you've entered your set points correctly. Sometimes folks will transpose torr and millitorr, not realizing that 1 millitorr is in fact 1/1000th of 1 torr. So 1 torr corresponds to 1000 millitorr. So what if your gauge is controlling, but not quite as expected? Maybe you can't achieve the set point or your pump seems improperly powered. If you have your gauge and valve hooked up to your vacuum system, but the pressure in the system is not being controlled, first we make sure that the gauge is reading vacuum accurately. We can't control a system that we can't read, and you can always review our slides, which we will be hosting on our website after this webinar, and return to how to troubleshoot vacuum readings. Connect your sensor to the largest part of the system away from the valve. If the valve is too close to the sensor, excess air in the body of the valve that is released when it activates will briefly cool the thermocouple and cause erratic readings. Remember, all of our vacuum readings hang on what those heated filaments inside the sensor does. So the valve has been holding on to a bit of air that otherwise has been evacuated from parts of the system. And then when it opens up, a puff of that air will come out and instantly provide a bit of gas to temporarily cool those filaments inside, which can cause a reading that jumps up and down in time with the sensor opening and closing. Also, we'll want to make sure that our high set point is higher than the low set point, obviously, and also ensuring that our vacuum hose is the right size. Too large hoses or those with too thin of a diameter wall can be pulled closed by the force of the vacuum generated by the pump. And we can always assist you in choosing the right hose for your pump and your application. We'll see if your pump is appropriately powered. A good way to do this is to perform a base pressure test, which can be done with, for instance, our bullseye precision gauge happens to be popular for that application. With the KF25 flange sensor, can be connected directly onto the inlet of your vacuum pump and be used for a quick base pressure test. An underpowered vacuum pump will not be able to achieve the set point at all, and an overpowered vacuum pump will struggle to hold vacuum level at that set point. Also, if a controller is unable to approach the set point, there may be a leak in the system. Make sure to check all of your threaded and flanged connections. For a bleed valve malfunction, always ensure that the PID settings are tuned appropriately for the system. We have conveniently hosted a blog on this subject called PID for Vacuum System Automation at digivac.com, which can be referenced at any time. So now that we've gone over some basics of troubleshooting and repairs for our gauges and thermocouple type gauges in general, it's time for the Q&A. Over the course of this webinar, I hope you've been submitting your questions in the chat. Alrighty then, I'm just going through some of the questions that we've received. We've received one that states, when testing sensor resistance, oh, and by the way, this is an excellent question. Thank you very much for bringing this up. I'm sorry, I don't have the names attached as we're working on Pabade, I believe could perhaps be the name. I apologize if I've mangled that. I'm used to having my own last name mangled from time to time as well. The question states, when testing sensor resistance, check test lead resistance first so it can be subtracted from the measurement. 2.9 ohms may actually be 2 ohms plus 0.9 ohms test lead resistance. And this is an excellent point to make. We, in particular in our facility, use the Fluke 87V, I believe it is, multimeter. And we've personally tested the resistance of those leads to be about 0.2 ohms. Now, what we're really looking for is not so much exactly a resistance measurement within a certain range, but to see that they're electrically connected in the first place. Around 1.5 to 2 ohms happens to be the standard, but what we're really looking to find out is whether we've got an open loop in between any one of those pin combinations. But this is a great observation that should absolutely be stated. It's very important, of course, to figure the resistance of your leads into whatever measurements you're trying to take with your meter. Alternately, another problem that we've sometimes experienced with this thermocouple type sensor is you may get a resistance that's so crazy high that while the sensor may technically be electrically connected, it's not going to read vacuum because the resistance of that one filament in particular is just so high. Attempting to excite that filament with the circuitry of our gauge isn't going to get a proportionate response. So I'd like to say thank you for that. That's a great observation. And I hope we were able to clear it up a little bit. We have a message from Brian Mess. Thank you, Brian, for chiming in. When cleaning with acetone, should you rinse with IPA, isopropyl alcohol, after using acetone? We have not found this in particular to make a difference in the functionality of the sensor. If the interior of the sensor is dry, there should be no problem with the readings after just using plain old acetone. We've cleaned many sensors with just IPA, some with just acetone, and we've not seen the need for an IPA rinse after using the acetone. So you can certainly feel confident in using simply acetone if that's what you've got. We have another message from John C. John, this is an excellent point, one that we should have outlined before. Can you go over the difference between the Agilent 531 sensor and the 536? Great question. The 531 and the 536 are both fully welded stainless steel. The only difference in between them is that the 536 sensor has a small shield, which we call a baffle, that very partially obscures the thermocouple wires inside the sensor. In the 531, you may peer in and see the little X made by the filaments inside, but the 536 has a baffle that partially blocks those off. Now remember, we can't isolate them completely because they still need to respond to the amount of gas that's in your system, but that extra little shield can really make the difference between a contaminated sensor and one that more effectively resists contamination. We recommend the 536 for folks mostly in the oil distillation and purification fields because sometimes it's just that last little line of defense that might keep your sensor cleaner, which is always a good idea. Now, the 531 and the 536 are electrically identical. They function the same way. They read the same range of vacuum with the exact same accuracy. The only difference is that little baffle in there. I have another comment, Pabade, excuse me, please forgive me if I'm pronouncing your name wrong. It says, it seems like a good idea when soaking a sensor in IPA or acetone to cover the opening to prevent solvent evaporation. A glass microscope slide or slide cover should work for acetone. This is another great observation. We haven't particularly experienced all that much evaporation, especially seeing as the amount of time that the solvent is in the sensor doing its thing is usually about an hour. That typically, now just anecdotally from my experience, doesn't seem to be enough time to constitute a significant enough evaporation in that it would cut the efficiency of the solvent. Although there's certainly nothing wrong with doing that. If you feel inclined to prevent whatever small amount of evaporation might exist, that is more than fine. Really, all that matters is that you're using the correct type of solvent for your purpose, and you ensure that that solvent runs clear from the body of the sensor when you finish cleaning it, and that you don't attempt to use it until you've either dried it in ambient air or dried it under vacuum. Oh my goodness, I'm so sorry about that. It seems that not only have I butchered your name, but your name is Paul B. Excuse me for that. Those are some really excellent insights into exactly how the sensor cleaning process works. So I'd like to thank you for that, and please excuse me for my misunderstanding of your name. If anybody else has any additional questions or needs clarification on anything that we've discussed, I'll give y'all a minute or so to chuck them in. But in the meantime, I'd like to thank everybody for joining. This has been not only a learning experience for me, but hopefully one for you folks as well. I know that I really value the opportunity to be able to share the 8 years of vacuum technology repair and maintenance and theory and troubleshooting and everything that I've learned here over the years. I'd like to also say that please don't hesitate to contact us for live technical support. You will almost certainly get me on the phone. We're here from 8:30 a.m. to 5 p.m. Monday through Friday, Eastern Standard Time. So feel free to give us a ring. We've got our number on the right-hand side, and we'll always be glad to walk you through any setup processes or troubleshooting processes that you may need. We have another question from Paul. Just real quick before I continue with my wrap up, have you had any issues with filament corrosion? This happens not as a result of cleaning, we've found. As a matter of fact, we recommend frequent cleaning in order to prevent filament corrosion. We typically have seen corrosion of filaments in super dirty processes where the sensor has maybe been allowed to sit without cleaning for a large amount of time. For instance, we have a customer who typically works with food processing where they do a lot of freeze drying. Sometimes those sensors will be left to sort of marinate in their own contamination over time. And in that situation, the filaments can corrode and either break apart, or their resistance can become so atypical that the gauge can't be calibrated to read vacuum correctly. So we consider regular cleaning and maintenance as a great way to prevent that corrosion, although that corrosion is rare. So we'll post our webinar, this webinar, to our website for all future reference to anyone who might be interested. I'd like to tell you to stay tuned for upcoming DigiVac webinars. We've got a few in the pipeline as we speak. We'll be doing a full-length demonstration of the sensor cleaning, as well as different demonstrations, for instance, with our rotary evaporator, which I'm very excited about. So feel free to let us know what other topics you're interested in. And I'd like to say good afternoon to everybody, and hopefully we'll see you next time. Thanks.